Now let's talk about assemblers, what it does. Okay, so let's take an example of an assembly code, and don't worry if you don't understand this assembly code, what it does. It is not important. Okay, so know what this assembly code is doing, or it does not need much of an assembly programming concept at this point. Okay, so from this, what we have learned so far, we have like some labels like loop L1 and L2 here, and bunch of instruction with these mnemonics and followed by the arguments, etc., etc. So assembling this code to generate an object code is a two-step process. Number one, first step is find the memory location of the labels, and secondly, combine the numeric equivalent of opcode register specific combining numeric equivalent of the opcode and register specifier and labels and all this stuff, right? So it's a two-step process. So pass one is your address of the label generation, pass two is your object code generation. So what I mean by address of a label, right? So that's first thing, let's understand. And if you look at these instructions, each of these instructions, like 1, 2, 3, 4, those instructions, each instruction will ultimately generate an 32-bit machine code, right? And they will be placed inside the memory. Like when you invoke an executable, what happens essentially, that that executable machine code, list of machine code, is copied into a part of the memory. Okay, so copied into the part of the memory. So your first instruction goes in one memory address, and then second instruction goes in successive memory address, and so on and so forth. So each of these instruction essentially is stored in a memory address. Okay, so you can think of a label as a name of that address. Okay, name of the address of what? Like name of the address of the next instruction after the label. So that means a loop, a string loop, is referred to the address of the instruction which is immediately next to it. So this, for our case, it will be LW R5 R2 0 cross 0. So for this instruction, wherever that instruction is copied in the memory during the execution of this program, your loop is that address. Okay, so another point to note here, it really doesn't matter where this next instruction is. I can have bunch of comments and new lines and white spaces in between a loop and the next instruction, but what the point is that those new lines, white spaces, comments will be just filtered out, and it becomes a compact code like this, instructions, a series of instruction like this, and your label will pick up address of its immediately next instruction. So it is not address of Louis, it is not address of this load word, but it is immediately next instruction address. Same for L1 is the address of this instruction, add I R0 R5 0 cross 0, and L2 is a code, let's say for push. Okay, L2 is, let's say, called instruction called push, with that wherever this instruction is copied into the memory, that address is assigned to L2. So that's the concept of the label. So label is a name or reference name to an address of that corresponding instruction. Okay, so in pass one, okay, this step one, let's see how it does it. Let's first index your instructions. Okay, instruction 1, 2, 3, we have like 18 instruction in this piece of code. So what happens is each time it goes and it reads in, assembler reads in from line 1 or line 2. I should not tell it line 1, line 2, it's really instruction 1, instruction 2. There can be like again lot of comments in between instructions, lot of like white spaces, new lines, etc. So it's just filtered out. So let's call it an instruction 1, instructions 2 instead of line 1, line 2, line 3. So instruction 1 is parsed, like it's broken down into pieces and see what can be done, etc, etc. So let's say it comes down to the instruction 6. So it parses, it breaks down into different keyword like loop, LW, R5, comma, 2, 0 cross 0, etc. And they are called a lexib. In terms of compiler study, we call it them at lexib. Okay, so we breakdowns are lined into lexibs. And then assembler sees, well, this specific line has a label associated with that. So for instruction 1 to 5, they didn't have a label. So assembler will just ignore them for time being in this first step 1, right? First phase, first step, it will ignore any line that is without any label. So if there is a label, then what happens? It creates something called a symbol table, and inside the symbol table, at this point it enters that symbol name and an address relative to this code. Okay, because at this point you really don't know what is the address is going to be for this instruction, right? You don't know yet. So we just get, okay, this is for my instruction 6. Okay, that's what we entered there. Similarly, we have instruction 14, we have L1 symbol table, and its instruction number is 14, and then L2 instruction number is 16. That's what we create a symbol table now. Okay, so pass 1 or step 1 is all about creating a symbol table. That's a lookup table. It contains a symbols as a key, and its value is what instruction number it belongs to. And let's call it an relative address. Okay, relative address, because it's an relative to the very first instruction, number 1. So relative to this instruction, it is the 6th instruction, L1 is the 14th instruction, push is the 16th instruction. That's what goes in your symbol table. Now at this point, let me also explain something called a forward referencing. What does it mean? So look at these movements. So after 6, we have an enter. This symbol table has a symbol called loop, right? And then when it goes and, for example, parses 13, which is JMP L2, L2 is referring to a label which is not yet inside that symbol table. So that's why it is called a forward reference. If you see instruction 10, it is also an example of the forward reference, because when it goes and assembler parse this line, your L1 is not yet there in the symbol table. So this is a forward reference. Okay, so this is a forward reference concept. And instruction 18, if you look at, when it comes to referring this loop, it is already in the symbol table. So we can we know already what is that relative address of that instruction is, and that is then just a reference. You can call it, this is a reference to a loop. It is not a forward reference as such. Now let's talk about this next step, this object code generation. So at this point, we constructed this symbol table, which is a lookup table, right? Now again, assembler start parsing each of this line and combine them into the corresponding machine code that we already know how to do it, right? We look at the opcode, we look at the function code, we put the RSRT and this immediate, sorry, for here is this case RT and RS, and then the immediate values and how to put them in the certain format given, already predetermined format, and put those binary values and make a 32-bit machine code out of it. So that process assembler takes up and make the corresponding machine code. So it does for second instruction, third instruction, fourth, fifth, sixth, seventh, eighth, ninth, and when it comes to the 10th, what happens, it is referring to a label L1, right? Now it goes and refer to the symbol table, pick up the relative address value, and somewhat combine that information into machine code. What is the detail it does, we'll discuss later. Okay, how this 14 gets into this specific instruction PNE R8, R9, L1, we'll discuss it later. Okay, we'll discuss it later. But for time being, just take it as granted that it looks up for that symbol's relative address and combine that information somehow into your machine code. All right, it generates that. So similarly, it goes for next instruction 11, 12, 13. Again, it refers to symbols, so it goes back and look at the symbol table, retrieve the relative address, combine that information into this instructions machine code, and then instruction 14, 15, 16, 17, and 18. Now it also need to refer to the symbol table, picks up the relative address, combine it somehow into the machine code. That somehow part will come later. Okay, maybe 2 or 3 lectures down the line, we'll come to that. So that is how it goes and generate your assembly, your machine code. It combines the step 1's symbol table created into it and combine that information into step 2 when it is generating the machine code.